Problem 16.90 involves a 3.5 kilogram slender rod AB right here, and a 2 kilogram slender rod BC, which is right here, and they're pin connected at B and by a cord AC right there. The assembly can rotate in a vertical plane under the combined effect of gravity and a couple M applied to the rod BC. So the rod BC has this couple applied to it. Knowing that in the position shown, the angular velocity of the assembly is 0, and the tension in the rod AC is 25 newtons, tension in the cord AC, excuse me, is 25 newtons. Wants us to find in the A part the angular acceleration of the assembly, and in the B part find the magnitude of the moment. So I'm going to call MAB is a 3.5 kilogram mass, and BC is 2. The initial angular velocity here is omega equals 0, tension is 25 newtons. L1 is 300 millimeters, and L2 is 400 millimeters. So L2 is the distance from here to here, and L1 is this distance right here. Basically, this forms a single rigid body rotating about C. Even though it's not all rigid body, this is going to stay tension in this line here. So in effect, that's what you have. So we can talk about the acceleration of point D down here as being alpha K crossed into minus 300 millimeter J, and that's equal to then 300 millimeter alpha I. So the acceleration of this bar right here is going to be equal to 300 millimeter alpha I. We're going to do a free body diagram on AB next. Right here it is. We got the tension, we got the force of gravity down, we got a BX and a BY. Forces out here, this pin connection. We're going to do a Newton's second law for this AB bar, but we're going to look at the sum of the moments about B right here. So that's going to be equal to I bar alpha plus then you'd have your R bar crossed into MA bar. But now for this bar, the center of mass, this is already pointing in the I direction, so there's not going to be an R bar. There's no moment arm, so this term is going to be 0 right here. And so what we have then is the force of gravity that about B right here is trying to create a positive moment, so at 400 millimeters. And then you have T sine theta here, where theta, T sine theta is a vertical part of this tension. So you got that acting at 800 millimeters across here, and it's negative because it's trying to produce a clockwise moment. And that's all got to be equal to 1/12 MAB 800 millimeters squared alpha, 1/12 ML squared then alpha. You solve for alpha out of this, you get 9.929 radians per second squared. You get a positive number out of it, so it means it's got a counterclockwise alpha. Now we're going to look at the entire body now and calculate the moments about C. So the moments about C can be written as I sub C times alpha. Well, what is my I sub C? Well, I sub C would be whatever moment of inertia I have about the center of mass here and in parallel axis to there, and then a moment of inertia about the end of this rod right here, which would be a 1/3 ml squared. So that's why I have a 1/3 MBC L squared. And what's my L right there? Well, it's 400 squared plus 300 squared. And then I have a 1/12 ML squared for this term right here. So there's a 1/12 MAB L squared. And then I have the parallel axis theorem to go MAB times this distance squared, which is 300 millimeters squared, and then times alpha. So what's all creating this moment about C? Well, you have a moment right there about C that's counterclockwise, so I'll put that M in. And then you have this MBCG right there at 200 millimeters, because that's halfway across there, 200 millimeters in. This right here doesn't produce any moment about C because it acts through C. So we just have this, and when you solve for M, you get 10.13 Newton meters.